All right, so this is the Tetrahedral Planetoid. I have made a video about this where there's a 3D print available, but 3D print's not available anymore because the Shapeways shop goes down. So I'm just going through this and showing off how this whole thing works so that other people can make some and hopefully be able to use this for procedural generation of other planetoid style objects. I'd like to make this into a game at some point, but for now this is just going to be a walkthrough of this file. You can find this at triap.com. And it takes you right here, and here's a website, and you can download it right here. That's the Blender file. And it's got some pictures of the 3D print and all that stuff. I won't go through this because you can go through it yourself if you'd like. We are here for this model. So this has got multiple different layers. Layer 1, and this is just in Blender, you push the number keys at the top of the keyboard. So number 1 is the all the pieces of the buildings and things. And number 2 is the boats and the water. And number 3 is the plants. So pretty straightforward. And if you hold down Shift, you can press 2 and 1, and you've already got 3. And so now here's the whole thing. Very nice. And the shape of the object is, so Escher's famous for making optical illusions and impossible geometry and stuff like that. But most of his stuff was actually not impossible geometry. It was just odd perspectives or weird projections and things. And this one turns out not to be even a weird projection. It's just an odd object. But it's totally possible in 3D. In fact, as you saw from the website, I have actually 3D printed this thing and have a real physical object of this in my possession. And you might think, oh, but these are AI generated or something. But no, it turns out it's impossible to get AI to generate an image of the Tetrahedral Planetoid, and God knows I've tried. These are the closest things I could get to it generating a Tetrahedral Planetoid style image. And I think the reason is because all the image generators are trained on images that are taken on Earth, and Earth is very large, and so all the buildings are going straight up with the top toward the top of the image and the ground at the bottom of the image. And so when you give it something like the Tetrahedral Planetoid, it does not know what to do with that, and so it just kind of dies. It gets a little close. I mean, this is not too bad, but it's not great either. So yeah, see, it's kind of close. Anyway, so no, it's not AI generated, and as far as I know, AI will probably never be able to generate something like this. I mean, never say never, but it's optimized for the stuff that most people generate, and this is kind of far enough off the beaten path that I don't think AI is ever going to get around to generating this kind of geometry. So what makes this geometry unique? Well, we've got, if you push number 6, you see the base tetrahedron, and if we push Shift 1, now we can see that the geometry is almost entirely enclosed within this tetrahedral surface. And you can see there, that's the basic shape. So tetrahedron is a shape with equal sides and equal edges. And it's one of the 5 platonic solids. And so here we see all the sides are length 2, and it's got vertices and edges. So one of the ways that I made this, when I first started off making it, I was just making it all in one perspective. This was over a decade ago. This is almost 20 years ago. I started making this 3D model, and it evolved over a period of time. But eventually, I gave up on that and started doing it in pieces. And so here's what it looks like now. You can see we've got the base model. Turn all these off. Okay, there we go. This is the base geometry. So you can see this face here and this face here has some more detail because these are the faces that I modeled before I started doing everything separately. But I have moved a lot of the detail over to the other faces. So that's the base geometry. And this, you can think of this as the edges. So we've got to turn this off. So you can think of this as the edges of the tetrahedron. You've got these edges here, and each of these edges is defined by a line of buildings that bridges between two faces. So you can see these are, go back to this, there we go. These building edges here are bridging between the two faces. Doesn't have any detail really on the points, on the vertices, and doesn't really have detail on the faces themselves. They do have some on these but not much. It's just kind of the edges connecting the vertices together and connecting the faces together. So that's the edges kind of geometry. And then on top of that is built the 4 faces. So these 4 faces and these 4 vertices. And each one of these is instantiated on the base geometry so that you end up with the whole thing. So if it's kind of hard to see which ones are which, but if I grab some of this and move it around, you'll see very quickly. Oh, no, you won't, because I've got the base instancing turned on. There we go. So that's the bottom face there. You can see all those pieces are kind of moving around weird. And so just for practicality's sake, all you need to know is these are the 4 vertices, and these are the 4 faces surrounding this area here. And this is all on layer 4, appropriately enough. So if you want to mess with the face that's got the big hole in the middle, this is the face to do it on. And you've got all these little stairs and stuff and buildings and things. And you can see all these windows sticking out. And if you hide that, they're actually sticking in, and that's because they're using Booleans and stuff. So I'll go over all that in detail, but that's the basic overview. Is layer 1 is just the buildings, layer 2 is just the water and boats. And again, these guys are all, these are fun too. All right, I'll go over all this later. Layer 3 is all the plants, and the plants are pretty basic. It's just instances of these objects that I've moved around, and I did a little bit of geometry nodes magic on some of them, but basically it's all just rotated around this center point, and that's using if you press period and hit 6, then that's the 3D cursor, and that'll allow you to rotate stuff around. So that's how you move things on a tetrahedral planetoid. Instead of just grabbing G and moving them, you press RR and rotate them around the center of the planetoid. And then layer 4 is, of course, the construction stuff. And there's some of those geometry objects in there that are used for the plants, and they're just kind of hiding in the middle of the planetoid. So that's the overview. Let's get into the details. Where to start? Probably on how each of these vertices works. So the vertices are built around 3 faces that come together. No, that's too hard. We'll do the faces first. Faces are built around, each one of these is up in the Z direction, and the center of all these objects is at the center of the planetoid. So you can see the pivot point is there. Shift S 2 snaps the cursor to the pivot point, and now you can rotate these around the Z direction, and that all works properly. These buildings themselves are generated using some geometry nodes. So here you can see I've got a few little vertices here, and if I move these vertices around, I can change the shape of the building, but you notice that it's not actually making the top a weird shape. It's staying level, and that's because of all these geometry nodes modifiers on there. So let's just jump into those. So this guy has a number of geometry nodes modifiers. One of them is the Spherize geometry node. That's pretty straightforward. It takes the geometry. It says if you're not, let's see, in the selection, if you're not selected, no, true. Oh, that's just, what is this? Fake named attributes. No, I'm not sure what selection is. Delete that geometry, and then it grabs the position value, the length of the position value, and the length of the position value is basically the distance from the center of that object. So it takes all the points and finds the length of that, the position, the length of the position. So it's the distance from the center of the sphere, from the origin, from the object origin, which in this case is the center of the sphere. And then it divides that by the number of points. And so that's just the number of, or no, that's the mean value. Oh, that's the mean value. Yeah. It divides it by the average, and then scales each one by its position vector. So it basically averages them all out radially, and then sets all the positions of those guys. Let's see. Not true. Selection. Delete geometry. This is doing something. I'm not sure what it is. But anyway, this sets the position so that you get the position of all these vertices is averaged out radially. And then I do a simple screw modifier, and that's just rotating it around the z direction. You can change this angle to change how big. You can see over here how big that. We should go back into the layout so that it looks a little nicer. And go over to this. There we go. So in the top window here, you can see that you can change the angle so that the building is smaller or larger. You can change the number of steps so that you get more or less steps. I've been keeping them pretty low, but you can increase it without any problem. And you can also subdivide these without it causing any problems because it spherizes it after. So if you've got a little bit janky, it doesn't matter. It smooths it all out and makes it all a flat surface on the top. So that's nice. So the little spherize geometry nodes, then screw modifier, then another geometry nodes that I made, which is called radial extrude. And so let's turn off all of these and just go into this so you can see what this does. So that's the spherize. You can see how it, well, a little bit. There we go. You can see how that spherize averages out the position of all those points. I'm gonna bring this back so it's not quite so wonky anymore. And then there's the screw modifier. It just makes a surface. And then here is the radial extrude. So radial extrude, similar, pretty simple. You get the geometry input, you get the target radius, and that is a property of your geometry nodes. You can change this target radius. You can see how that gets larger and smaller. And that's all the inputs, and then just takes the position, gets the length of the position vector. Again, that's just the distance from the center. Divides the position by the scale factor, which is calculated based on your target radius. And then you capture your geometry, and you, let's see, scale it, set the position of all the geometry, flip the faces. This makes the bottom surface. And then, oh no, extrudes it in. Then you set the position, and you just have an offset distance of 0. So it doesn't move it at all, but then it grabs the original points, sets a position based on your scale factor, which is the target radius, flips the faces, so that's the inside surface. And then if you have join turned on, no, that's just always true. Oh, I see. It only flips it. Yeah, it only flips the faces if it's inward, if the distance is going in rather than out, because sometimes you want this to be outward instead, and so it should work there as well, and it does. You don't end up with bad faces that way, except for that face. All right, well, you don't end up with as bad faces. I'm not sure why I put that in there if that doesn't work, but it seems to work. So you join it, and then you merge by distance to join the original face on the inside to the new face. And then you output the geometry. So that's radial extrude, and you can see that instead of extruding it normal to the face, although in this case it is normal to the face, it extrudes it toward the center of, or away from the center of the object. So that's the radial extrude, and then I've just got some simple booleans. This boolean does an intersection with the windows and doors and things, so that's just a window object. Window cutouts, 30. I think fast works now, but before fast didn't work very well. So anyway, so that just does a simple boolean, and then an auto smooth. And there you have it. So that's how those buildings are made. A lot of them, not all of them, but a lot of them are made that way. So you've got these blocky buildings, and they're generated using that exact same process. You've got some points for your surface. You've got a spherize a screw modifier, radial extrude, Boolean for the windows, and then maybe a couple Booleans for different windows and things. And there you have it. And these guys are same kind of idea. Spherize, screw modifier. They don't have a Boolean, but they've got the radial extrude. So all these objects are all using that same tool chain of screw, geometry nodes, and Boolean. So all these blocks, that's how those are made. I used to make them, like I said, by rotating the view, and then I was rotating around the center of the view. It was all very fiddly. But this is way, way faster, and Geometry Nodes makes this a lot nicer. So like this sloped roof, I don't have a spherize on it because then that would make this not sloped, but I do use the screw modifier. And then instead of using the radial extrude, I use a solidify modifier. But same kind of idea. And these guys are, I don't know if they even have, oh yeah, they've got a spiral arc arrangement, spiral arc array. So that's fun. Let's take a look at that geometry nodes real quick. So it's basically, you've got a count, you've got a mesh line, you rotate each one by the count number, and then you combine them all together and instance them on points and realize the instances, and you're done. So it's a basic, radial array. Only this one has a little bit of difference. Let's see, what's the difference in this? Spiral arc. Oh, because this one has a base scale. Okay, yeah, so you can scale these guys. You can tell this to scale it up or down, and it'll make a radial scale. So if we increase this, yeah, so this is what I'm using for the stairs. Okay, so I just reused that, and then the scale is how high you want this thing to be placed, and you can also rotate it more or less. So there we go. We've got all those points, and yeah, it rotates it around. So we'll see more of that later. Let's see if this undoes. It does. Great. So yeah, so those are the faces, and they're all basically using the same process. Some of them have more geometry built into them than others, so if you hide that, there's not a lot of geometry here. There's a few of these buildings and things, but it's mostly the base geometry, the base object. Some of them have much more, like the new ones, like this side over here. So if you hide this, all these buildings are generated using the process I just went over, using the rotate, the spherize, all that kind of thing. But the stairs are one of the exceptions, because the stairs are they're tricky. So the original model, the original woodcut by Escher, has the stairs with they're much bigger. The step size is much larger than would be normal, and they're also inconsistent. Some of the step sizes are fairly large near the center. Some of them are pretty small near the edges. It wasn't perfect. He wasn't perfect. He wasn't using a computer. He was eyeballing it and trying to get the scale right, or trying to make it look right, or trying to make it so that he could actually carve them. Because if he did the real scale size that was reasonable for something of this scale, he probably wouldn't have been able to carve them. It was just too small for his woodcut process for lithography, or lithography, whatever. Treography, graphography, reproduction. The way he was reproducing them, he was cutting them into wood, so they had to have a feature size that was larger than the wood grain, or the wood size that it would accept. So all that to say, these stairs have all been normalized. So all the stairs have the same height, and if you tab into this, you'll see that it is just 2 points. It is not anything more than these 2 points. This point is at the height of, so if you snap this to the closest, now we've got the stairs coming right to the edge of this edge here, and then we could rotate it. I got to get the center in the right place. There we go. We could rotate it around, so now it's on the surface here, and we can move how far out the stairs go. And then with this one, we can move how high the stairs go. So it's all procedurally generated based on these 2 points. And I am really happy with how that works. And to see how that works, let's take a look at the geometry nodes. So we've got 2 geometry nodes here. The main one is the rotary stairs. And the rotary stairs includes somewhere that spiral arc array. Yeah, it's got the spiral arc array geometry nodes inside, and it also has the extrude rotate geometry nodes inside and the radial extrude geometry nodes inside. So it's got all of those inside here. And basically what this does, I've forgotten how this works, but basically how it works is you've got 2 points, you know you've got 2 points, so we have a named attribute and it's called mask, and one of these points has the mask attribute set to it. One of them has the start. So if we unselect all and select the start, it's got the start vertex. So this one is the start vertex, and then it just assumes that there's only one other one in there, and if you extrude this, then it averages out all the other ones, I think. Yeah, I think it just averages out all these other points to get the end point. So you could like extrude out to here and extrude out to here and get like the average of the position of a bunch of different points if you wanted to. I never, don't say never, but I don't think I did that. So it's got this mask attribute, and the mask is set in here as start. So that's start. And so you can set this to whatever you want, and that'll say, okay, that's my starting vertex. So that vertex, I'm going to use that for 2 things. One is I'm going to get the position of that point, and I'm going to get the length of it. That's the radial distance out. So this is the distance from the center that the start of the stairs is. And then you also multiply it by just the z component, because this always assumes that it's rotating about the z vector. Stairs are calculated based on the start position, and it gets the multiply, it gets the length of that vector, and that's the height off of the distance around the center. Then does the dot product and divides that vector, and that's our calculated total angle. I left some notes for us. So that's a calculated total angle that we're going to be including in our stairs. And if you need something more than 90 degrees, I think, then you have to make multiple stairs. I don't allow for super long ones. I didn't need it in this. I mean, all of them are pretty short. So you can see that the start point, you always want the x to line up with the start vertex. So that's why I was going all weird there. If you move the x too far off the start vertex, then it's still rotating it around that that local y direction. You can see that it's extruding it out along that local y direction. So you always want that vertex to be y value of 0. Yeah, okay, so that's the calculated total angle. So you can't get over 180, and it always has to go in one direction. If you want it to go in the other direction, then you just scale this whole thing y scale of -1. So if we set this to 1, then it's rotated around the other way, and that's how you get it to rotate in the opposite direction. You just set the scale to -1. Oh yeah, so I guess I don't need the invert normals anymore, because the new version of Blender automatically inverts the normals when you have only one dimension with a negative scale, so that you don't end up with the inverted normals. So like all these guys, they've got this inverted normals geometry nodes on there, and probably you don't need it anymore. All it does is just takes the geometry and flips all the faces. So probably I could get rid of all those. In fact, I probably should, but I'm not going to right now. Right now I'm still talking about this monstered stair geometry nodes. So we've got our calculated total angle. We use that in a couple places. We use it to figure out how many steps we want. We have a maximum value of 1 for calculating the step length, because you always want at least 1 step. And then you've got the number of steps in the total angle, and that's, let's see, multiplied by the tread offset. So the tread offset is a little tricky as well. Yeah, this one's got a tread offset set. So this guy right here has a tread offset of 2. And so if you reduce this to 1, now the tread comes right to the edge of this piece of geometry. Set it to 0, now the second step comes right to the edge of that piece of geometry. Set it to -1, now the third step comes right to the edge. So it's basically just setting how far the setback is for that tread. So there's 4, same kind of thing. It just sets the offset. But the math there, you have to do some offsets in here. So you have the maximum step length, and then you have to multiply it by the tread offset to get, and then subtract that by the calculated total angle in order to get the actual number of steps that you want. And so then this is the spiral arc array that I talked about earlier with the roof tiles, and that takes the count for the number of steps, and then you subtract out the offset. Sometimes if you've got an offset, sometimes you want the whole value because you want to know how far you're supposed to be rotating the whole thing. Here's the height offset, tells you how far down to extrude. Here we go. That's easier to see here. So height offset tells you how far down to extrude the stairs. Each step is its own watertight volume. There we go. That's what I'm trying to say. That's all I'm saying. So the height offset tells you how far down to extrude the whole thing. And that gets set here. So you do the spiral arc array of all of those steps. Well, no, we've got to extrude rotate first. Extrude rotate. Can I go into this? I can. Here we go. So extrude rotate is how each step gets made. Basically takes the mesh point, it extrudes it by a vector of 0, so it just doesn't move it at all. And then it sets its position by rotating about the z-axis by the it rotates the position vector around the z-axis by the angle that is set here in the group input. And I think that's all it does. It just does that once. Seems like it would do that twice to get. Oh yeah, it does. It does do it twice. So it extrude rotates it, and then extrude rotates it again, and then extrude rotates it again. So I guess I've got it 3 times. That should be the tread width or something, right? Yeah, width right there. So the width is divided by 100 arbitrarily. So this width value doesn't actually correspond to, where's the width? Yeah, it doesn't actually correspond to any real value. It's just set arbitrarily. And then, oh yeah, it extrudes it once for the step, for this, in this direction for the step, and then it extrudes it twice for the 2 points, one here and one there. So that's what the 3 are. So one of them is extruded here. Node Y rotate extrude. Okay, yeah, I got lazy. I just made 2 versions of this. One of them is around the Y-axis, and the other one is around the Z-axis. So this is the Z-axis version, and the other ones are and they're identical. They're just around. This is around the Y-axis instead of the Z-axis. I couldn't figure out how to set that in an input, so I just did it with the. I just did it by making 2 different extrude rotate geometry nodes. I'm sure the geometry nodes guys would be very happy to point out how I could improve all this, and I'd be happy to see how I could improve it as well, make it more performant, all that kind of thing. But in the meantime, this works, and this is what we've got. So anyway, it calculates the total angle. It calculates the total number of steps by figuring out how far down it is. So it takes the average of all the other points that are not the start point in the start group, and then gets the average distance there, and then calculates it and inverts it and adds -1 and sets the maximum value and rounds it to the nearest value, and that's the number of steps that you get. And then it does all that in the spiral arc array. That's how you get those steps themselves, and then it realizes them, and then if, oh yeah, realize all is always turned on, and then it radially extrudes all of those surfaces to the target radius, which is calculated over here by taking the average value of the final point and then and averaging all that out. And so if you set this to 0, I believe, yeah, you'll get just one step up. And then as this goes negative, you end up with negative steps, and you don't want that, and so you set it to positive, and then you get positive steps. So that's how that all works. And if you want to make it a spiral, so it's always going to rotate around the z-axis. But if you want this whole thing to be straight, as it were, then you need this to be a z value of 0, so that when it rotates around that axis, it ends up going straight instead of going on a spiral, if that makes sense. You can see there it's lined up with a z of 0. And as it goes higher up, it becomes more and more like a cone, and less like a circle or something. They're always conics, but you know, a circle is a conic too, so if that makes sense. Man, this is why this geometry is so difficult to talk about and think about. All right, let's see if I can undo all this. Undo, undo, undo. There we go. So you'll notice that these have a little bit of an extra feature where they have this arch underneath, and that has another geometry nodes called the radial shrink-wrap. And so if we turn that off, it's just the normal rotary stairs like we saw before, where it's got the height offset, and they just extrude downward using the radial extrude. But then if you turn on the radial shrink-wrap, then it does that, and that is because it's targeting this thing, so we'll get both of those. There we go. So the radial shrink-wrap, much simpler, basically takes the object, takes the target object as a relative geometry, does a target geometry raycast for every point in the original mesh, and then if you hit, then you select that point and you set the geometry position to the hit position plus the normalized offset value normalized along the direction of the position, which is the radial distance. And the reason I did that is so that I could use the radial shrink wrap and have an offset, so I could offset it up or down, and that would extrude it in or out from that hit surface. So that's pretty handy, and that lets you make all those arches. So that's how all those arches are made. So that's the radial shrink wrap, and I think that's basically all of the fancy geometry nodes. No, it's not true. I still have the relative instancing things. Those were a real pain. All right, so that's all the faces. The vertices are basically the same, except they're 3 different faces all coming together, and so I had to be a little bit careful about orienting the objects so that the rotation of these surfaces was about the 120-degree rotated vectors. And I forget how I got those values. I think I may have taken the original tetrahedron and like brought it over here and made some dummy objects or something. But practically speaking, I would just select another object that was already oriented properly and then rotate it 120 degrees to get to the other side, which is how I got all these surfaces. But same kind of idea. You've got all these stairs. They're all correctly rotated about the center of the object, and they're all using that stair thing. Oh, and I wanted to show off. So you can select all objects in layer 4, and if you hold down Alt, you can set the tread height to whatever you want. Let's zoom in on this guy. Let's go to the layout. Here we go. Now we can see a bunch of different ones at the same time. So here we're looking at these stairs, and we're looking at these stairs, and this guy can be looking at some other stairs somewhere else. There we go. And so if I hold down Alt and modify the tread height, well, I don't want to go that way too much, but you can see you can make the tread height much larger or much smaller. If you make it too much smaller, then it makes it really, really, really small, and then it crashes Blender, so I won't do that. But yeah, you can modify the tread height. You can just select this and 0.05. Now they're very small steps. Hold down Alt, select this. I think for the 3D print I use 0.3. So I made the stairs much larger because otherwise they wouldn't print out. It would just be like a smooth surface without any steps to it at all, which isn't interesting. And then I think 0.1 is the correct height for the scale of all the doors and windows and things. But that's a nice feature, that you can change the tread height of everything in the whole model all at once. Very, very nice. Oh, that's still messed up. Well, we'll just pretend that didn't happen. So these guys, they're sitting over here, and how do you get them to instantiate onto your base mesh properly? So you've got this object, and I've got a relative instance geometry node, of course. And the relative instance geometry node looks like this. So it takes the object, it multiplies the location by -1, and then it sets a mesh line with 1 point, because I couldn't figure out how else to do it, and then instanced the object on those points, and then scaled them all by the absolute value of the scale factor of the original object, and then runs it through a reverse rotation geometry node, which I had to invent. I think they've got a real one now that's built into Blender, but I had to invent that one, and then realizes the instances and then joins the geometry to the original geometry, and that's how you get that object. So the inputs are the collection, the Vert3 parts, and then the relative object is the Vert3 base. So the Vert3 base, these are called Vert 1, 2, and 3, and 4. So that's Vert 4. This is Vert 3. This is Vert 2. This is Vert 1. And one of these objects is the Vert 1 base. I think Vert 1 is down here. Yeah, so the relative object is Vert 4.002. So that's this guy right here, Vert 4.002. So this is the base geometry, and then any other geometry is relative to this object. And then that object is also, where's our Vert 4? Is also this object. So all this geometry, you can edit it in place because it is this mesh object in place. And then it instantiates any object that's relative to itself but over here, relative to itself but over here. So that you can model in place here, and then if you want to model in place over here, you can do that too. So everything gets modeled in place, and then all the sub-objects that are instantiated relative to it, like this guy right here, you can just model this in place right on this thing, and everything is editable. Now you can't edit this surface over here, because when you go into edit mode, it doesn't show up because the geometry isn't in there. So you do have to go back to this Vert 4 parts collection and find that, and that is Vert 4 parts. There it is. So if you select all these, we've got some stairs, we've got some Vert 4 geometry, and that all gets instantiated around this object. So that's what that relative instantiation thing does. And the magic about it is this reverse rotation node, which because all the objects are rotated XYZ, in order to reverse the rotation, you have to reverse the rotation in opposite order. So you have to separate out the rotation vector. So you get your group input, which is your vector, and the vector is the rotation vector. and then you multiply by -1, and then you separate it all out, and then you combine just the z in and rotate the instances, and then combine just the y in and rotate the instances, and then combine just the x in and rotate the instances, and then you get your output of your instances. So it's very silly, but it works, and that allows you to invert the rotation. I think, let me just search here for rotate utilities, rotate vector, Euler to rotation, rotation to Euler, utilities, rotation. Let's see, utilities, rotation. All right, axes to rotation, invert rotation right there. So that's what that does. But they didn't have it at the time when I was working on this, so I didn't use it. I rolled my own, had to roll my own reverse, my own invert rotation. Anyway, so that's the relative instances. So that's how I'm doing the relative instances with the vertices on the corners. So each of these is just the same mesh node as whatever the big mesh object is over here. And then I can model in upright mode over here, and then instantiate it back on top of this over here, because like the LLM, or it's not a large language model, it's a large image model or whatever, but like the generative AI, I too have trouble thinking in like 120-degree angled upside down mode. And so all of this is modeled in right side up mode, the vertices over here, faces over here, and then it gets combined back on the base model. Then the base model has so it has those 4 vertices, which are the separate meshes, and then the base mesh has 4 of those relative instance geometry nodes running on it that instantiate all 4 of those common surface faces on them. And that, I think, is the whole thing of how the tetrahedral planetoid model actually works. So if you were going to go and make your own tetrahedral planetoid from scratch, you could do it pretty straightforwardly using these tools, using the all these Boolean objects that I've set up with the spherized stuff. Oh, I should show off the spherized a little bit more, because it's actually used in some of these. So like this, I believe has spherized. Yeah, it's got a spherized point applied to it. So that way you can, if you wanted to add a little balcony over here or something, you just extrude this out. You don't have to be too careful about where you put it vertically, because the spherize handles all of that and make sure that that surface is spherically level, so that you don't have to fiddle with it. So now you've got an extra little thing sticking out here, and you don't have to worry about it being level. So that makes it a lot easier, much more easy to work with than I was working with. So yeah, the spherize is really handy on its own, not only for straightening out lines, but also for straightening out entire surfaces. And you can always apply this too. So like you take this, Shift D to duplicate it, Control A to apply it, and now all these points are going to be exactly at the correct height because the spherize has been applied. So if that matters to you for whatever reason, you can apply the spherize pretty easily just by doing that. And then I would leave it in the stack just so that you have got access to it, so you can work with it later. Yeah. So I would be super pleased and excited if someone were to make something like this that generated this whole city kind of thing, just based on this mesh. So you could take a mesh like this and then move the points around, and it would still generate a city on it, or use different solids, and it would still generate all those radial surfaces and points and things. That was kind of my original dream, and I don't know if I'm ever going to get there, but I'm sure some wizard, some geometry nodes wizard out there could figure it out, and that would be super neat to see this whole thing be able to generate it based on any arbitrary mesh it just, you know, generates it around the center of the object, and then you can move the points around and see the whole city kind of constrained to the shape of the mesh. Very tricky city generator kind of thing, and I don't know if you'd need it to do, what are some of the really cool, like this kind of thing, right, where the tower blends perfectly into the wall here, then that blends perfectly into the archway. That might be a little tricky. Maybe not. Maybe it would be easy. I haven't really tried to do it parametrically, but I feel like it could be done with, especially now that I've got all these tools set up with all the stairs and the different shapes and things pretty well set up now. It wouldn't be too hard. I feel like it wouldn't be too hard to make one that generates it based on a base mesh like this. But that has not happened, and until it does, this will remain, as far as I can tell, the best and only 3D model of a tetrahedral planetoid ever made. And even though AI is getting very good at 3D models, don't know if it's ever going to be able to do something like this. I tried to feed it into Trello and some other 3D modeling from image, like feeding the original image and the render of the 3D model image, and was not able to generate anything convincing. It just kind of blew up. So I think this is going to remain for a while at least a pretty good touchstone of real human 3D modeling capabilities, because if you try to feed this into an AI, the AI doesn't know what to do with it. But it's also pretty straightforward for a human to look at and say, oh yeah, that totally makes sense. I see how that works. You know, it's all just radial around the face centers and radial out from the center of the object, of the planetoid. So again, you can get this online at tetrahedral.triop.com, and it'll take you to the page where you can download the Blender file. And maybe before I upload this, I'll clean up the model so it doesn't have all those inverted normals and stuff. But yeah, that's the original one. What it looked like before I put all those procedural stairs in, and you can see that some of the stairs have more steps and some have less, and they don't line up perfectly well with the edges of the landings and things, whereas now they line up perfectly. All right, I'm gonna stop talking.